Hello everyone, thank you for joining us for today's webinar. My name is Neil Foley and I'm the Applications Engineer at RISE. Today I'm going to be talking about best practices for orienting parts to achieve various effects that may be important to you. So I'll start with an overview of some of the different things we'll discuss. Essentially, I will be going over a variety of different things that you may want to optimize when preparing your part for printing, and there are different things to consider for each of these with regard to how you orient your part. So I'll be covering a few points on each of these topics. They include, you can see, strength, ease of support removal, material usage, speed, avoiding warpage, precision and tolerance, surface finish, and markup quality. So the focus of which of these you'll want to concern yourself with the most will depend on the application and the most challenging properties of the specific part that you're working on. So we'll start with orienting for strength. So some of the things that you'll have to pay attention to, some of the considerations to make when you're working with a part that has features that need special attention with regard to strength are, first of all, considering the difference between the strength in the X and Y directions versus the strength in the Z direction. So for most thermoplastic 3D printers, the Z direction will be quite a bit weaker than the X and Y direction, and because of this, you'll want to always make sure that you don't have any fragile features that are oriented vertically. In the case of RISE, our process ameliorates this issue quite a bit, but it's still something to pay attention to. Our Z strength is about 90% as strong as our X and Y strength, so orienting parts for strength is not as important, but it may still be something that can help you get that little bit of extra strength that you need for a fragile feature. So some of the types of fragile features that you may need to pay attention to include pins or thin flanges. So those are some of the challenges. Some of the ways of addressing these things include orienting your fragile or strength critical features horizontally. So this would mean whatever direction is sort of the moment arm along which your fragile feature is most likely to break. You want that to be oriented such that it is parallel with a horizontal plane. This way you won't have to deal with the slightly lower strength of the Z direction, creating a weak point on that feature. Another thing to consider is increasing the in-plane cross-sectional area by changing the angle at which the part is printed slightly. So for example, if you have a narrow pin that is oriented vertically, you don't necessarily need to turn that all the way to a horizontal position. It can also help just to turn it to an angle, perhaps 45 degrees, and this will increase the cross-sectional area of each layer that's extruded, and that will help it gain a fair bit of strength, which in some cases may be just what you need. So what I'm going to do now is look at a part in our software that this type of thing may be useful for. So you can see a part here that has some very thin walls in both this upper section and this lower section here. So you can't see into it, but if I enter slice view, then you'll see that there are only a few tool paths that are developing the walls of this vertical tube. So one of the best ways of making sure that this part would be strong would be to make sure that both this narrow tube and this narrow tube, the vertical and the horizontal, are instead both horizontal. So this would be a good orientation if you are really concerned with the strength of these two narrow components. This is not necessarily the best orientation if you are optimizing for things other than strength. So that's what we'll talk about next. So another thing to pay attention to is how easy it will be to remove supports from a part. So some of the different things you'll have to pay attention to include the number of support structures that you have. If you have a lot of supports, then it's going to take more time to remove them. And in some cases, it can also be more difficult the more you have. You'll also want to pay attention to the volume of a support versus the model support interface area. So what this is referring to is that if you have a very short support that covers a lot of ground, then that would have a large model support interface area compared to its volume, because there would be a large area where the support is touching the model. However, if you have a tall and narrow support that only touches the model at a small surface area, then that would be much easier to remove than trying to break the interface for a larger interface area. Another thing to pay attention to is internal cavities and through holes. If you have internal cavities or through holes, it can be fairly difficult to access the support on the inside, and this can make it more difficult to remove it. A special case of internal cavities is perpendicular holes, and I'll be discussing when we return to the software one way of addressing the issues that come up for perpendicular holes. So regarding reducing the support structure quantity, essentially what you would want to do is just look for ways of orienting the part that will eliminate how much support you need. So one of the best ways of doing this is to use self-supporting build angles, which will make it so that the bottom surface of a part is able to hold itself up, and you can eliminate all of the support structure that would have been built underneath it. Another option when considering the model support interface area versus the volume of support is to do exactly what I was describing earlier. Try to orient parts such that you have tall and thin supports rather than short and wide supports, and this type of support will just generally be easier to break off. And finally, regarding internal cavities and through holes, if you do have internal cavities and through holes that you expect to be an issue for removing the support from, then it's best to focus all your efforts on finding the right orientation for that, because you might find an orientation that optimizes other features, but if you can't get the supports out of the cavities in your part, then it's going to be a lot of trouble. So I mentioned perpendicular holes earlier, and one of the things you run into with perpendicular holes is that if you try to orient one so that it is vertically oriented and self-supporting, it will be impossible to orient another in the same way. So one of the things you can do is orient both of them to a 45-degree upward angle, and then what you'll need to do is actually reduce the self-supporting angle setting, and I'll show you what that looks like. So for this part we were looking at before, right now if I were to prepare this part, then the inside of both of these two tubes would be filled up with support, and it would be fairly difficult to remove the support from them. So what we're going to do instead is reorient it, and then what I'll do is turn this by 45 degrees, and now both of these tubes are oriented at 45 degrees. So what would happen now if I prepared the job is that these two tubes would still fill with support, and it might be a little bit easier than it would have been, but it still might give us some trouble because there's still going to be support through almost the entire thing. So what we can do instead is go to our prepared jobs, go to the advanced support generation options, and then you can see here that there is this option for making support for surfaces sloped less than some number of degrees. And the default value for this is 45.5 degrees, and this means that support will be produced for any angle less than 45.5 degrees. So if it's at 45 degrees, it will produce support. So all we have to do is change this angle slightly to 44 degrees, and now we'll see if we begin begin to slice the part, you can see there's no support on the inside there. And I can even enter slice view, and we can look inside, and now those are being produced without any support. Now again, this is something that maybe you'll want to consider if the ease of support removal is one of the main challenges that you're facing with a particular part. However, for some parts, you may have to find another solution. You can see here that this part is producing fairly narrow walls here, and they get wider the higher you go and eventually fill up like that. But this may not be a very strong wall here, and so maybe you don't want to exclusively focus on the ease of support removal in this case. So now we'll look at conserving material. So there are various reasons why you might want to be conservative with the amount of material you're using, especially if you are designing a part for printing that you expect to print in large quantities. If that's the case, then it can be useful to try to shave off as much material as possible so that you can save it for later prints. So some of the things that affect your material usage include the volume of support structures that are necessary for the orientation you've chosen, as well as the size of the raft and witness bar. So the size of the raft is essentially determined by the footprint of your part. So this will be any portion of the part that is touching the ground or touching the build plate, as well as any supports that are called down from your part and also reaching the build plate. So the things you'll want to pay attention to for solving these issues include minimizing support usage, which can be done by minimizing the height of overhangs. So if you have an overhang that can be reoriented in some way to reduce the amount of support that's needed underneath it, then it's good to try to take that approach. And also, as I've mentioned a few times, self-supporting build angles can eliminate the need for support entirely from a section of your part. And as I mentioned with the raft and witness bar, essentially all you need to do is try to minimize the build height and the footprint. Now, these two factors that are affecting the decision you make regarding orienting your part sort of work against each other in some cases. So it may be that minimizing the build height and footprint will make it very difficult to minimize the height of overhangs or produce self-supporting build angles. So in some cases, you may have to play around to try and find the optimal solution. So now we're going to look at another part. So this is a fairly simple part with a pyramid-like structure and some overhangs here. And the orientation that it's in would probably be a pretty standard one to print in. This is what it's imported as, and it's probably the one a lot of people would choose. However, in the special case of trying to conserve material, there are some decisions that you can make that will actually reduce the amount of material that you need. So I'm going to hit slice view here to bring up the support. And you can see that in order to hold up these overhangs, there's a lot of support built around them. And in addition to building the support up under these overhangs, it also increases the size of the footprint versus what was just touching the build plate originally. So now I'm going to try reorienting this. I'm going to flip it upside down. And now because the footprint of just this bottom X is much smaller than the footprint of the entire part, and because the walls of this pyramid are self-supporting, when I enter slice view now, you'll see that there's hardly any support needed at all, and the raft is much smaller. So if this is a part that you expected to build many copies of, then printing it in this orientation could help quite a bit with reducing the amount of material that you need to use. The next topic is orienting for speed. So this would be trying to optimally reduce the amount of time it takes to produce a part. So some of the things you need to pay attention to here are additional time added to the process due to building support and the witness bar. Also, One of the important differences to pay attention to is the print speed of contours versus infill. So contour is the outer edge of each layer of the printed part, and the infill is the section within the contours. And finally, you may want to pay attention to using solid versus honeycomb infills, which is something primarily, it's a decision primarily related to the volume versus the surface area of the part. So I'll start with the support and witness bar build time. You'll typically want to do a similar thing to what we did on the previous slide, which is reduce the amount of support needed. To reduce the witness bar build time, all you need to do is try to find an orientation that will make sure the highest point on your build is as low as possible. Also, if you're building parts with different heights, then what you'll want to do is place the tallest parts closest to the witness bar, so that once the shorter parts finish, the print head doesn't have to travel back and forth over the shorter parts in order to get from the witness bar to the taller parts. If you keep all of the tall parts close together near the witness bar, then the carriage will have to do the least travel. So regarding contours and infills, one thing that you can try to do to reduce time is make sure that you're using as little contour as possible. The contour will move quite slow, whereas the infill can move quite quickly. So one of the things you can do to try to reduce the number of contours you need and increase the amount of the part that will be produced with infill is try to sort of reduce the portion of your part that has vertical surfaces. So this is sort of a difficult thing to wrap your head around, but I'll demonstrate it once we get back into the software. It's essentially trying to reduce the footprint if you were to project the part horizontally onto a wall. And then finally, regarding solid versus honeycomb infills, one of the things you want to pay attention to is that honeycomb will typically be faster because it involves less extrusion. However, the infill for solid parts is sometimes a bit faster in cases where you have a lot of thin or porous sections, and this is because honeycomb uses 3 contours while solid fill uses only 1 contour. So if most of your part is thin or close to an edge or a side surface, then you'll spend a lot more time producing contours slowly and less time doing the actual infill. So because of this, it can be better to minimize the number of contours you're using by choosing a solid fill. So now I'll look at this part. So as I mentioned before, one of the things you'll want to perhaps pay attention to is reducing the amount of vertical surface area that you're printing. So some different orientations you might try could be like this. The problem with this is that this entire wall here and this entire wall here and all of the vertical walls around the whole thing are going to be produced with a contour type of printing, which will be quite slow. So you can see that since these walls aren't very thick, a pretty significant portion will be contours, and because of that, a large portion of the volume of the part will be printed at a slow rate. So the other option would be to print it like this, and as I mentioned, you can now see that if you were to project this against a wall, or at least the X by Z wall in this case, then it would have a much smaller footprint against that wall than the previous orientation. And using this orientation means that only this small portion at the bottom, as well as the full portion of this wall, will be printed using contours, whereas most of the rest of the volume of this lower portion will be printed using infills, and that can speed up the print quite a bit. The next thing I'm going to talk about is thermal contraction or warping. So one of the things you can find is that if you try to print large flat parts or very bulky parts, then as you print, the hot material that is applied to the top will pull on the material that's underneath it and warp the edges upward. And this is usually caused by wide, unbroken horizontal bottom surfaces. So if you have a surface on the bottom with no separation, no holes, you just have a large mass, then that region is going to probably warp up and give you some trouble, both in terms of producing the geometry correctly as well as hitting the tolerances that you're looking for. So some of the things you can do to ameliorate this problem include breaking those wide surfaces into separate layers by printing them vertically or sloped. So this can eliminate the amount of hot material that you're adding with each layer, and because of that you won't be stretching the lower layers quite as much. Each layer will have a smaller footprint and it will be affecting a smaller region directly underneath it. So I'll explain that a little more once we get back to the software. And then another thing that's a bit counterintuitive is in some cases it's often good to minimize the bulk near the bottom of the part. So most of the warping is going to primarily affect the bottom of the part because that's the part that is on the build plate for the longest, so it's going to have the most material added on top of it, whereas bulk at the top is only in the print for a shorter portion of time, and so it's not going to have as much material working to stretch it. So I'm going to look now at a few other parts. So you can see this part here has a pretty wide, unbroken bottom surface, and because of that, you could expect that it would probably warp a bit at the edges. And so a good approach to printing a part like this would be to reorient it, either like this, so that it doesn't have as much bulk on the bottom, and so that each layer has a smaller footprint and it won't be affecting the layers underneath it quite as much. Or you could even go more extreme and print it all the way upright like that, and that would even have a stronger effect. On the next part, although it is a wide bottom surface, it isn't continuous. It has a lot of holes in it that break it up, and because of this, you don't have material pulling at the layers below it over quite as much distance. You have small segments that will be pulling just at the material directly below them, but a lot of the mass is sort of isolated. So this type of part should be quite okay to print in exactly the orientation you see here. The other thing about this part is that this is one of the ones that is similar to what I mentioned, where a whole lot of the part is very close to a surface, whereas with this part you only have a small portion of it that's at the edges. On this part, the entire thing is close to an edge because there are so many holes through it, and because of this part would probably take a long time to print, especially using a honeycomb fill, because there are so many contours to produce and because contours take a longer time to print. For the next part, this is a very bulky part, so printed in this orientation, you would be pretty likely to see some warping at the bottom corners. So I would take a more extreme approach with this one and print it directly vertical in order to minimize that type of warping. So now we'll get into orienting parts for accuracy and tolerance. So some of the things that can pose as a challenge for this topic include thermal contraction, which, because of the warping that it can cause or the contraction that it can cause, can change the dimensions of your parts, and that can throw your parts out of the tolerances that you may be aiming for. So some of the specifications of the way our printer works include a specified tolerance of 0.003 of an inch or 0.005 of an inch per inch, whichever of those is greater. So for very small dimensions, you could expect it to be within 0.03 of an inch. For larger dimensions, you would have to count how long that part actually is and multiply it by 0.05 of an inch to figure out how precise you can expect it to be. Also, there are some differences between vertical resolution and horizontal resolution, and how you need to deal with them. So the vertical resolution is limited to a sort of quantized set of possible quantities. So we have two resolutions, either standard or fine. That's 250 microns or 125 microns. And because you can't go in between those amounts, it may be useful if you're trying to get very precise with a certain dimension to avoid putting that dimension in a vertical orientation, because there are values that can't be hit in the vertical direction. Now, typically, vertical dimensions will be overshot slightly. They'll be on the higher end of this specification. With regard to horizontal resolutions, they are not quantized in the same way, or at least they have a much higher resolution of quantization. So you can get much more accurate or precise values. However, typically with horizontal resolutions, you will see undershooting, often due to the thermal contraction. So some of the things you can do to address these are, one thing that we recommend is to use a scale factor of 1.005 if you're really trying to hit precise dimensions. And this can eliminate some of the contraction that you see from the warpage, and it can help your horizontal values get closer to the proper target. Another thing you can do is to orient your vital dimensions vertically and then scale it slightly so that the value that you're aiming for will fall into one of the quantized values that can be hit by a vertical resolution. One of the things about the vertical resolution is that although it overshoots a bit, it can be very precise. So if you are willing to scale apart very slightly, it may give you better resolution. Next, something to consider for orienting for optimizing your surface finish of your parts. Some of the things that can pose as challenges include stepping, which is when you have a shallow slope, and in order to fill out that slope, the quantized vertical resolution needs to break it up into layers, and if it's a shallow enough slope, you'll be able to see the layers broken up. So one of the things you can do to improve this situation is to just try to eliminate any shallow sloping by orienting parts in a way that you won't find any shallow slopes. So this can often involve orienting parts in sort of strange or unexpected orientations in order to eliminate any slopes that are close to horizontal. Another thing that you can do is, it's okay for a slope to be close to vertical. So if you have just a single slope or a few slopes that are close to horizontal, orienting them to be vertical or close to vertical will often solve the problem. Another important topic is curved surfaces, especially on bottom surfaces, and it can also, you can also find quite a bit of stepping if you have sort of shallow curves, and you can try to solve that using a similar approach where you orient those curves to be more vertical facing. With regard to bottom surfaces, if there are curves or shallow slopes, the sort of stepping can often produce some not very good looking support structures, and it can be good to try and eliminate any shallow slopes or curved surfaces on bottom surfaces just to reduce the possibility of getting bad looking support like that. And our final topic will be trying to orient parts optimally for getting good markup accuracy. So in this case, you have a few similar challenges to getting good surface quality, and that includes stepping. It's best to avoid putting a markup on a very stepped surface because you'll be able to see the breaks in the markup and it won't look quite as good as if it were on a flat surface or on a curved surface that's close to vertical, which doesn't have as apparent stepping. Another thing to be careful of is inverted slopes. Inverted slopes would be slopes that are approaching an overhang, and in some cases, inverted slopes, you can find that as the markup is printed, the ink is being jetted over the edge of the slope and falling either down to the raft if you're lucky, or down to other portions of the part that are underneath that slope if you're not so lucky. And so one of the things you can try to do to avoid that is just to make sure that your print heads are aligned by running a calibration, and that can reduce that problem a good amount, but you can also in some cases solve that problem by reorienting the part so that that slope with a markup, that inverted slope with a markup on it, will not be oriented such that the slope is inverted. Finally, when applying markups to bottom surfaces, the ink does not show up quite as well as on top surfaces because it is printed on top of the bottom surface, and so it's showing through a layer of material. And so if you are looking to put a markup on a bottom surface like this, it's better to try to stick to orienting the part so that that markup will be facing either outward horizontally or face it straight upward. So that's all I have for this webinar. Thank you all for joining us. If you have any questions, I will be sticking around for a few minutes and you can enter them into the chat box in the GoToMeeting window. If you have any off-topic questions or would like to start a conversation, you can always reach me at applications@rise3d.com. So other than that, if you don't have any questions, please have a nice day.